Hello, everyone. My name is Devon Beckman, and I'm a master's student at the University of Guelph. This is my project on increasing soil organic matter using long-term switchgrass cropping systems. So I did this under the direction of Dr. Adam Gillespie and Dr. Sarah Buchanan with help from Richard Gressick. So not all organic matter is equal. When we're talking about soil organic carbon, we have to divide it into two distinct portions, palm and mound. The main difference between these is their size. So particulate organic matter, or palm, is greater than 53 microns and is what we like to say roughly sand-sized. And it consists of primarily decomposing plant matter, so roots and previous litter. It typically has a higher C to N ratio, which usually results in a little bit longer time in the soil. And what we like to see that it typically resides in the soil for a couple years to a decade. When we contrast that with mineral-associated organic matter, which is a lot smaller, roughly clay size, this is made up of primarily microbial metabolites and necromass. It is so small that it is adsorbed to soil surfaces like clay, and they can remain in the soil for centuries. And we like to call this stable carbon. This is carbon that will be locked within the soil profile and not released back into the atmosphere for up to centuries. While they are very distinct, both are important. So palm is a driver behind soil respiration, short-term decomposition of soil organic matter. That's typically going to be where the nutrients that the plants use for growth are coming from. Whereas mound, the rates of mound within a soil indicate the ability for it to sequester carbon from the atmosphere long-term. Like I said, stable carbon. And this is a main contributor to the fight against climate change. So why are we looking at these with a view from switchgrass? As you guys know, switchgrass has an extensive and deep rooting system, way deeper compared to traditional cash crops. And it is very high yielding, even on marginal lands where other stuff may not grow too well. And due to these factors, it has a very high carbon input into the soil, theoretically. So the objective of my study, we had three hypotheses. The first one is that mound and palm will be highest in forested areas, pretty typical due to the high biomass above the soil in forested areas. And then this would be followed by switchgrass. And then lastly, conventional agriculture would have the least amount of stored carbon. My second hypothesis is that mound and palm will be significantly different between cultivars based on soil texture. I'll go later into that. And then hypothesis three is that mound and palm will be higher at depth compared to traditional cash crops. And once again, that is due to the extensive and deep rooting depth of switchgrass. So we had four different switchgrass field trials, two in Ontario and two in Quebec, and we chose these field trials due to their distinct soil texture. So our first site was at Simcoe, which is, if you've been there, it's pretty much all sand. We also, right next door, in Elora, which is a silt loam, St. Matthew de Blois in Quebec City, which is a clay loam, and then La Pocatier, which is 2 hours north of Quebec City, and that's pretty much clay. So our methodology, we took a modified post pounder and we took 1 meter deep cores, and we looked at three specific switchgrass cultivars, so Cave and Rock, widely used upland cultivar, cold tolerant, robust establishment. We looked at Big Rock, which is a newer hybrid with high biomass and stand persistence. And then finally Sundance, which is a newer hybrid, vigorous rooting and strong yield potential. So to prepare our samples, we took the soil core and we divided them into 4 different depths, 0 to 15 centimeters, 50 and 30 centimeters, 30 to 60 centimeters, 60 to 100 centimeters. And then that's a typo, but we passed them through a 53 micron sieve to separate the portions into mound and palm. And then we used a combustion analysis machine to obtain the carbon percentage of each of these fractions. And then we performed some statistical analysis on them to look at our hypotheses. So result one of our first hypothesis about land use and the partitioning of the carbon stored by the stands. As you look at the graph, we do see a visual pattern on both mound and palm, indicating that our hypothesis was correct. However, this was not significantly proven statistically. Our second result, this is a pretty busy chart, but it's the results of our second hypothesis, where we look at how cultivar determines carbon storage in the soil based on soil texture. And what we found was that that had really no effect on how the carbon was partitioned in the soil, and the mammoth palm rates were due primarily just to texture of the soil. And our third result, the depth, which is some of the most interesting stuff, is still in progress. We have to do an additional step of our analysis due to high carbonate rates in the deeper levels of our soil. So an early takeaways, switchgrass may only be slightly better than traditional cash crops at sequestering atmospheric carbon. We're hoping that once we get the answer to our third hypothesis, that the deep rooting depth will prove to be a little bit more significant. And then soil texture determines carbon partitioning, and the cultivar choice may only fine-tune it slightly. And then here are some of our acknowledgements. Most important one in the bottom right corner. Thank you.
Thanks so much, everyone. I'm really happy to present. These are our results from the project Devon is a part of. There's 4 of us that have been working on this. And what I'm presenting today is a lot of work done by Sarah Willow Buchanan, who just had a baby. And so she's on maternity leave. And what a wonderful thing. She did really great stuff. A lot of what you're seeing here is a presentation that she would have prepared for another meeting for the Canadian Society, and then some of the newer material as we are collecting it. So whereas Devon was talking about some of the more physical fractionations, looking at the organic matter quality, what I'm going to talk about today are 2 sort of total carbon numbers. That we're also going to talk about contributions and analyzed through sort of a reasonably sophisticated approach using carbon isotopes. And then we're also going to look at carbon stability by, programmed pyrolysis. Is this okay now for the volume? Perfect. So the overall idea behind this is that we're looking at the different cultivars and also comparing the different soil textures in the same sites that Devon studied to look at the depth distribution and the stabilization. So I see it's thermal stabilization of these soil carbon pools. And so we've got these 4 ideas. The first one is we're going to look at the total organic carbon stocks at these different cultivars. The second one is the particulate and mineral associated, which that's Devon's, we just saw. The third one is to look at the thermal stability, which is sort of a proxy for whether it's biodegradable or not. And then the last one is we're going to look at the contribution of switchgrass-derived carbon using these carbon-13 isotope signatures. So I'm going to present 3 of the 4 sites today, the 2 that are near here, so Elora and the Simcoe Research Station. And the third one I'm going to present is way down the river in Quebec in a place called La Pocatière. We've got 3 contrasting textures. This is why I picked them. Simcoe sand, here at Elora is a loam, and down the river is a clay. We also picked these 3 sites because they've got good replication for these different cultivars. They all have cave and rock, big rock, and Sundance, and that's why we wanted to pick them. So there's a picture of somebody you already have seen today, and Stephen as well. Those 2 guys were a great field team. I would say that the banter was unmatched. It was so much fun. So we collected these soils using one of these soil coring devices and then segmented them 0 to 15, 15 to 30, 30 to 60, and 60 to 100. Did the normal thing that we normally do, sieving, grinding, and so forth. So I'll start right away and talk about, these are the total carbon stocks. Now, generally speaking, when we are doing any of these sorts of stock calculations, we have to assume a certain depth. So in this case, I believe we did a 15 centimeter depth. Some people pick 30, it doesn't matter. The idea is here you're quantifying the amount of carbon that's going to be in, I'm sorry, my mistake. I got confused. What we do is we quantified the stock in those different depth increments. And what's very interesting is that site by site, we found that there wasn't really a big difference in the cultivars, which is interesting because they all have different biomass yields, but we found that the total stock in these soils didn't really change depending on the cultivar. Nevertheless, what we did see was that the cave-in rock and the big rock were the ones that had probably the most carbon that had been put in there. But the big difference was compared to the agricultural control. So each of these sites also had sampled next to them something that had been in row crops. Given that these are all research stations, there is always going to be some kind of agronomic trial, and so we would have been able to sample from those sites nearby. Most of the time it was corn and beans, and I believe down in Quebec it was, I think it was actually corn and beans as well. And so this to me is the really interesting thing that we found. There was a significant difference in that carbon accumulation when you were using these switchgrass varieties on these soils. It was most notable in the surface and I would say the middle depths, but it's quite texture dependent. And so what do I mean by that? What I mean is the lighter textures, which we have at the first two, SRS is Simcoe, so that's the sand. Second one is Elora, that's the loam. You would find that actually that carbon increase happened deeper in the profile. The clay soil, which is the bottom one, La Pocatière, the carbon increase happened, but not any much farther down than the 30 to 60 centimeter area, or sorry, 30 to 60 centimeter depth. I find this to be really important because there is going to be that sort of texture related increase in that carbon. And again, the clay was limited to the surface. I think if we pull all that sort of idea together, what we can see is that the carbon increase, particularly in soils that started with the low baseline carbon, because the Elora soils did have been farmed for a very long time, and so they are lacking in carbon because of that. The Simcoe soils are sand, and so they do have a limited capacity for that stabilization. That ties in very closely with what Devon talked about. Any of these sort of soils that are particulate dominated, which the Simcoe would be, the larger size, means that it has a reduced capacity to actually hold that carbon. And again, we do have this interaction with the texture and the depth. Okay, all right. So far, so good. Sorry, this morning I spent. I had to teach my course, so I'm still in sort of teaching. I'm going to keep asking, is everything okay? Do I have to have a check-in? Online teaching is a real bonus, but you know, nobody turns their camera on, and I don't know what's going on over there. Could be anything. Okay. This is objective 3. I'm skipping over objective 2 because Devon already did that. This is the idea of stability. And I should clarify, when I talk about stability, I'm talking about its resistance to decomposition. That ties in directly with this idea of carbon sequestration, but it also ties in directly with nutrient cycling. If you have decomposition, you have nutrient cycling. Now, we think that more stable forms of carbon are going to contribute to this long-term storage. But again, it's important to consider anything that might cycle more quickly. Now, I use a technique called temperature-controlled pyrolysis to sort of assess this. The gold standard, any of this sort of thing, is to actually put your soil in a jar and measure the carbon dioxide that comes off over time. But it takes 3 months. So I like to try to, this sort of thing, you can get an assessment that's kind of related a little bit more quickly, and it's a very good insight that you can get. So this kind of gives us the idea of the thermal stability of the organic matter. The reason it works, pyrolysis is heating but without oxygen. So instead of burning, that heat energy goes in and it cracks any of those organic carbon molecules and volatilizes them. If they're more stable, it takes more heat. And as it turns out, that stability and heat susceptibility matches quite well with what the decomposition susceptibility would be. So, the one thing that I also do is I calculate something called a T50. T50 just strictly means the temperature at which 50% of your material would have pyrolyzed. And if it takes more heat to do that, then that temperature is going to go up, isn't it? And if it takes less heat, then that temperature is going to go down. So what we tend to think of it is if you have more, well, here, this is my explanation. The temperature at which 50% is pyrolyzed. And on this graph, I'm showing you the results from the Simcoe. So these are the sands on the x-axis, and actually that's up at the top here. That's the temperature in degrees Celsius. And then on the y-axis, that's just the depth that the sample came from. And so if that temperature goes up, it means that that soil organic matter is more stable. So let's talk about what we actually see here. Those are the 4 different treatments we had. So 3 different switchgrass, Sundance, Big Rock, Cave and Rock, and then AgCon stands for the agricultural control. And so what do we see? Well, we see they all kind of tighten together. I would say that at the surface, and this is pretty normal, your soils are quite available for decomposition. That temperature is low. Nevertheless, the agricultural control is highest. This significance is not 95 or 5%, whatever you want to call it, but it is a bit higher. I wouldn't say that it is significantly different. But what we do see is changes starting to happen at depth. Ties in very well with those carbon numbers. What we see is that the agricultural control is now the most stable, but the stuff that's under switchgrass is actually quite a bit more available. This is very interesting because this means that that switchgrass, is moving material below ground. You're starting to see increases of plant-derived organic carbon that is more available, probably cycling more quickly at 30 centimeters. Let's look at Elora. Elora is the silt loam. You can see there's sort of an overall pattern that matches and that it's quite available at the surface and becomes more stable as you go down through the profile. That's quite normal. But what's interesting is that in Elora, you see that there's a divergence of one cultivar that kind of goes along with the agricultural control. That's the, they're all very similar at the surface, but at depth, 60 centimeters is the Big Rock and the Cave and Rock that appear to be pulling more available material down into that deeper part of the profile. Very interesting, different soil, a bit heavier texture compared to the sand, moving some of that stuff a bit farther down before you start to see an effect. The last one here is the clay. This is from downriver in Quebec from La Pocatière. This one's very weird in the sense that at the surface, the agricultural control is lowest, but the line shape, that's the word I use, from that green line, the agricultural control, kind of goes opposite and does something very weird. And so I don't really have an explanation for why that is, but I do see that there's quite a contrast with whatever is happening underneath the switchgrass. And what I see under the switchgrass is, in fact, in all 3 of those treatments at 30 centimeters, you've got a pocket of almost more available carbon. So it's, to me, it's showing that these switchgrass cultivars in that part of the world and in that soil are moving that material down to about a foot below the surface. So just to summarize all that, and I put the 3 different plots there at the bottom so you can be reminded. The sandy loam and the clay, they're the ones that showed the small differences at the surface. But the main differences that we saw were at depth, either at 30 or at 60 centimeters. And what we saw is that the switchgrass cultivars are actually moving that more available carbon a bit deeper. And to me, that indicates very strongly that there's some contributions to that root system, to the buried carbon. All right, checking in. Everybody's doing fine. I don't want any questions. All right, the last one, this is pretty interesting. And this is where Sarah Willow comes in, and she's got a lot of experience with doing these abundance carbon isotopes. You've all heard of carbon dating. That's radioactive carbon. Did you know that there's a third kind of carbon? Carbon 12 is the big one that I see everywhere. Carbon 14 is the one that's radioactive, and then this is carbon 13. It's something that we can use to trace things. And the reason it works is because depending on what plant you're growing, it will actually promote or favor the accumulation of the lighter carbon isotope over the heavier. As it turns out, corn, switchgrass are the kind of plants that actually have a different signature compared to most everything else that we grow around here. And so what we can do is with a very specialized instrument, we can measure the difference between those two isotopes and calculate what contribution switchgrass had to that organic matter in that soil. It's pretty wild stuff, I think. Those are all the numbers that are on there. Corn and switchgrass have a depletion rate of 16 thousandths, whereas the three plants have a, just everything else has a depletion rate of closer to 25 thousandths. I hope you're all remembering that 2,000 there. And I left that on here because I always enjoy it. Sometimes you put up some math on a slide, like, what is going on? But this is just to point that Sarah Willa knows what she's doing. I mean, I think she knows what she's doing. And obviously, math looks very, very intensive. And that was one of the ways that I guess the point being is that they have these models that they use that calculate the mixture. And so that they know what happened, corn, what happened in the soil before, you can calculate how much that corn or switchgrass contributed to that sort of mixture. So we're not finished this experiment, but we do have some preliminary results. This is what we see. These are all four of the sites, the same ones that that Devon was talking about. And what you see there are the depletions in carbon 13. So if you go farther up that scale, it means more switchgrass contributions. So we've got the three cultivars, we've got two different depth increments, but there's actually something a little bit weird. You're looking at that and you're like, wow, okay, first thing I notice, Sarah Willow, by the way, she really likes art, so she puts paintings in there, and I figure leave it in there. Who doesn't like a little bit of art? What we see here is some of them are really high, and they're all the ones that are deep. Well, that means that switchgrass must be pushing carbon really deep in the profile. No, it's wrong. What's happening here is that all of our soils are calcareous, okay? You all have limestone. Limestone is its own beast. Limestone actually is highly, highly, highly enriched in this material, so it's giving us a false positive. So what we're doing now is we have to actually fumigate, get rid of that material and remeasure them. But from what we've learned so far is the ones that are at the surface, yeah, we are starting to see these influences or these additions of switchgrass related carbon up to what have we got here? 12,000 milligrams per kilogram. So we are seeing that enrichment and we are seeing that occurs. So the conclusions that we've got so far, we are accumulating carbon. It's highly texture related, and we're starting to see this carbon accumulating at depth, which is what we kind of wanted to see. The cultivar selection actually did not really affect the stocks as much as we had expected, which is actually a good thing. It means that you can be flexible with how you, what is it is you want to grow. You have something that the biomass is more appropriate for whatever operation you're running. We're showing that the thermal stability as a proxy for biological stability is a bit lower at depth, meaning that we're starting to see that root-derived carbon accumulating at depth, and then we're learning more and more about the isotope data. One other thing I wanted to share is we do have a new project that is going to start up and running this year. We seeded some plots. So we've got some new not rotations, but some new plots seeded in Elora, in Simcoe, in Richtown. We put them in last year. We're going to be tracking the soil carbon, and we're also going to be tracking soil function. We're hopeful that it takes. So again, thank you. I want to thank you guys. I want to thank people from SOM. I want to thank Roger And I want to thank Richard, who's not here, who does all of our work. That's it. Gracious enough to leave 2 minutes for questions. Good.
Okay, hi Adam.
Hi, how are you?
Good, thank you.
Good.
So, in terms of the this research, you started 2010 on this soil, right?
Yeah.
But do you have other experience from the same land, like changing, say maybe 10 years or more than 10 years, how the carbon soil, organic carbon is changing with regard to the depth?
Right. No. And why, like you're asking, how would I know what happened?
In time, because
time,
long
yeah.
time, for example, you are talking about the switchgrass and three
Yeah.
different switchgrass cultivation happening.
Yeah.
And you started, for example, in 2010 in some land in Ellora,
Yeah.
and in 2025, what happened to that land in terms of the carbon with depth?
So I'll say that all those plots that we sampled from were not initiated by me, and so there isn't any legacy soil sampling done at depth. And so the only way that we're going to access that question you're asking is with the isotope work. And so we're still trying to work that through. Like the very idea that we're trying to see what's happening at depth is confounded with the lime and the carbonates in there. So we're still working through those samples. I think what you're asking is to compare the before and the after. I don't have before because I wasn't here.
So the land, like from which year right now you have that data, like 5 years ago or 6 years ago?
We sampled in 2023.
2020.
Yeah, 2023.
Okay, so
Yeah.
so it will take like a couple of more years to find out exact variation
Yeah,
that is
yeah.
happening.
and I think I know what Roger's gonna say.
Well, I just think it's a nice piece of research that Adam did, first of all. And that the results are consistent with what Michigan State University found, is that there was no variety impact on carbon additions. And with our breeding program, we're breeding for increased surface biomass. We're not trying to make the plant push more carbon into the soil. So maybe with breeding, we're doing nothing on soil carbon, we're just improving it because it's a better variety. But those plots are pretty nice plots that Adam sampled on there, 7 years old. They were established in 2016. He did the sampling in 2023, 7-year period. And the RC Big Rock is the same genetics as Caven. We bred it, but we didn't dramatically change the plant structure. So the results from the Big Rock and Caven Rock logically should be pretty close. And maybe we had 10% increase in yield or 15% increase in yield. So I think it's a pretty credible piece of research to support the existing understanding that variety is not really impacting soil carbon very much. And that the Wapaka site is the certain water, the water's close to the surface of that site. One of our varieties that doesn't like wet soils, doesn't grow very well, the RC Tecumseh. Okay. And so that's maybe why there wasn't as much rooting at a lower depth at that site. So it was getting a bit anaerobic. But they're very nice sites, those two sites in Quebec. And you know, the research shows that switchgrass does a great job increasing soil carbon, but the varieties new varieties are not necessarily impacting soil carbon in any way compared to the traditional variety, which is what they found in Michigan State.
So one of the other things, what I thought you were gonna point out also, that sometimes these older plots get overrun with smut.
Yeah.
And so these ones I think were pretty good. There was one at SOM that he presented, it's on the border. So some of them you get the older plots, but the disease has taken over. So it's not really, you're not getting 10 years of good input. You've sort of lost the last couple of years. Does that help?
Is like no, this is really helpful.
Okay.
That's why I am talking like in the end of 10 years or 15 years, you can quantify like how much of like, it's sequestering carbon. Actually, it is doing.
Yeah.
Once we do the study, you can directly say, okay, this much is the thing. It's not only on the surface, but also goes in the interior of the soil.
Yeah.
And which is happening inside. But that is good to know. But thank you very much. It's like a really nice
Okay, thank you.
study. Thank you.
Thank you.
All right, perfect. Thank you very much.